Today we're going to discuss the economics of condensate polishing and the physical piece of equipment, and as it relates to the investment in purchasing a polisher and understanding how the investment can pay itself back. Reuse or lose the condensate. That's very typical in a steam plant. Some of the questions we'll address today as it relates to condensate polishers: what boiler water treatment is required? What is condensate polishing versus softening? What are the challenges to condensate polishing? Why use a condensate polisher, and how does a condensate polisher pay for itself? The water treatment requirements are basically set by the ASME. ASME issues guidelines only. We're particularly focused, as it relates to condensate polishers, on iron and copper in return condensate, as these limits are very, very low even for low pressure boilers. As the pressure ramps up in a steam system, the water quality requirements become more and more stringent. Your makeup water or your domestic city or well water is generally treated, meaning it can be done with a cold water softener or no softening at all and just chemical treatment to your boiler feed water. Steam condensate, of course, can be treated chemically again through neutralizing amines, filming amines, and also a physical piece of equipment such as a condensate polisher. Why bother treating boiler condensate? Really comes down to scale and deposits on your boiler tubes. Fuel in a steam plant operation comprises about 75 to 80% of your spend in a typical steam plant or manufacturing operation. Having your boiler tubes clean, free of iron oxide, and copper deposits can pay for itself through your fuel expenditure, which will be much less with clean boiler tubes. Again, why bother treating your condensate? Over on the left here, all the deposits you can see are made up of iron and copper, magnesium, all the scale-forming ions that a condensate polisher would typically remove. Over on the right, you can see the thermal resistance. Once these deposits are on the tubes, the thermal resistance of the boiler tubes will decrease. A typical boiler tube has a very high thermal conductivity of about 310. And once these deposits, such as calcium phosphate, iron oxide, deposit on the boiler tubes, you can see the thermal resistance will drop by a factor of 12x or 15 all the way up to 20 with magnesium. ASME guidelines, again, as it relates to low pressure boilers, you can see some of the parameters listed here. Silica, again, not a constituent that a polisher would remove, but there still is a recommended guideline limit within a low pressure boiler of cycled water conditions that's internal to the boiler of 150 parts per million. The specific conductance, a neutralized conductivity of 5,400 micromos. Your alkalinity, again, that's cycled boiler water conditions of 700 parts per million in the boiler. Corrosion rate is mentioned simply because that's where a lot of the iron and copper come from in a typical steam condensate system. It comes from the corrosion of your black iron condensate return piping. And there is a recommended limit of 5 mils a year for that. Total iron and total copper, that is, these constituents, again, recommended guidelines by ASME, are in boiler feed water. Typically, your boiler feed water consists of city water makeup, well water makeup, whatever your source water you're using, and whatever condensate you're returning. So the more you degrade your condensate, basically the harder and harder it is for you to meet the ASME guidelines, the harder it is for a boiler opening, an annual boiler opening, to turn out with good results. Here we have a simple P&ID of a food plant, of their steam production cycle, using just a water softener, treating their domestic city water for steam production. You can see running through the softener, going to the aerator, to your feed water pump, into the boiler. You have your boiler blowdown consisting of continuous and bottom blowdowns, again for cycles control, and your steam out to use, which in our case is just jacketed reactors in a food plant. You have your return condensate coming back to your condensate return pump, and you see a divert valve, motorized divert valve. It's a three-way valve. This was put in as a measure, a low-cost measure, to divert condensate, contaminated condensate to drain so that the ASME limits for your return condensate aren't exceeded. Namely, copper and iron were exceeded in this case because of city water intrusion and oxygen intrusion into the jacketed reactors. You can see the polisher, once added, can eliminate the divert valve. While it's still shown here, it's typically put in as a preventive measure because it's a low-cost preventive measure versus a capital investment of a condensate polisher. While that's short-sighted, it's typically the first step a plant will take because you're talking orders of magnitude difference in money between purchasing a condensate polisher and installing a divert valve. The divert valve is put in simply to divert what we think is contaminated condensate on a general sense, meaning you have a conductivity sensor. It senses rather high boiler conductivity. In our particular case, it was set for about 50 micromole. Once that steam condensate hits 50 micromole, the divert valve would open up to drain and then stay open until the condensate conductivity would drop below 50. While this is a surefire way to meet ASME guidelines for your return condensate, it's somewhat short-sighted because of the thermal energy you're dumping down the drain. The condensate polisher will allow you to recapture that and essentially stop using the divert valve. One of the questions we're going to address on this is softening versus condensate polishing. A lot of people are probably more familiar with a cold water softener. They're primarily used in every boiler plant. Condensate polishers are typically not used as often. They're typically added after the fact. But some of the differences you can see, really just temperature in the resin is different. Materials of construction are going to be different. And the type of iron and copper that they're removing is going to be different. Condensate polisher operates at a much higher flow rate than a typical water softener. And this allows for the removal of copper and iron oxides because you're basically compacting the resin bed. The resin bed acts as a filter and an ion exchange device versus a water softener, which is strictly an ion exchange device and really cannot filter out effectively iron and copper oxides. You can see there's very little difference, except for the materials of construction, of a condensate polisher. On a water softener, we have a carbon steel line tanks, PLC controller. On the condensate polisher, we have much more expensive stainless steel tanks, unlined, and a simple electromechanical controller. So in a condensate polisher, it's typically wise to put the investment in the materials of construction, meaning the stainless, which is quite expensive, over a carbon steel vessel, which is typically used in a water softener. Again, some of the differences between a water softener and condensate polisher, they're both installed to meet ASME guidelines. We addressed some of the materials of construction difference. There are some others, as you can see. The condensate polisher is using ASME-coated steel tanks, steel valves, flanged piping, and typically adds a function of a subsurface wash. And again, the reason for that is because they act as both filters and ion exchange devices. You have to have a means to remove the iron and copper oxides, the crud, off the resin surface.